While talking about buffers, let us consider situations where there is some process variability. So if you look at this example of ski rental process, and in this situation we are assuming there is no variability. So five customers arrive every minute and five customers leave every minute. And in between each process we have room for maximum 50 customers. So that's the buffer or inventory that we have. This is a very well balanced process, and the process capacity is going to be 5 customers per minute. Now, if we reduce the buffer size from 50 to 6 for the second and third processes, each process can still process 5 customers. Since we have enough customers in buffer at the beginning, this process will have a process capacity very close to 5. Now, if the three processes have some variability in processing time, and if number of customers can vary from 4 to 6, so average is still 5, they can still take care of 5 customers per minute. But sometimes the process might be starved when there are no customers to work with, especially for the second and third process. And in some other situations they may have too many customers, in fact maybe more than 6, which the buffer cannot handle, and in that case the process will be blocked. So this is going to bring down the process capacity. Now when the process variability is even bigger, like in this case each process can process 0 to 10 customers per minute, so this is going to create a lot of problems in the flow of customers. Like if forms and pay processes close to 10 customers per minute and there's only room for 6 customers in the buffer, and the next process, let's say hypothetically if it is slower and is in the lower range, so it is going to bring down the capacity drastically. So with such high variability, if the buffers before second and third processes are increased to 50 again, so that is going to help improve the capacity significantly. And in fact, for the entire process, the capacity can be very close to 5. To summarize, when setup costs are involved, we can make use of EOQ formula to arrive at optimal batch sizes. But we need to be very cautious when we are converting setup time to setup cost. When there are even seemingly small price discounts, very large orders can be justified. We have seen that example. We know that setup times can cause process interruptions, and we can make use of inventory to decouple production. When there is a process variability, the capacity can be significantly reduced if we do not use buffers. Another point to note is we should not feed bottleneck with poor quality product because it will bring down the process capacity for the entire process. We should also avoid rework through the bottleneck, and it is always a good idea to check quality at source. Let's consider this example of scooters by Nova Cruz. So each scooter requires one steer support and two ribs. On the milling machine, steer support needs 1 hour of setup time, and processing time per steer support is 1 minute. Similarly, for ribs, this machine needs 60 minutes of setup time, and each rib requires half a minute. So for two ribs, it needs 1 minute. The key question we want to answer is what is the capacity of the milling machine? So capacity is defined as number of units produced divided by how much time it takes to produce those units. For example, if we have a process where we produce 12 units every 4 minutes, then we can divide 12 by 4 and get capacity as 3 units per minute. To obtain time to produce a batch, we need to add setup time with how much time it takes to produce entire batch. And then using this we can calculate capacity using this formula that we have seen earlier. Now suppose for Nova Cruz the production cycle is something like this. 100 steer support and then 200 reps, again 100 supports and 200 reps, and so on. So if we represent setup and production of 100 steer supports using this red rectangle, and setup and production of 200 reps using this white rectangle, then this is how the production cycle will look like. So we can define batch as a set of flow units and an interval of time such that these intervals of time are identical and repeat themselves. So that's what we have above. Now let's consider reps to be the flow unit defining the batch. So we have both white and red rectangles together defining as one rib batch. So there are two things that are happening in each rib batch interval. One is production of ribs and the other activities that do not produce ribs. We are going to call them as setup time for rib production. So the setup time within each rib batch interval now includes all the time in which ribs are not produced. That can include setting up the rib production. It can also include any idle time when worker or machine they are not working, and it can include production of other things such as support in this case. When we consider a batch size of 200 ribs for each batch and do the calculation for capacity, we get 0.625 ribs per minute. And a similar analysis for steer support will yield a capacity of 0.3125 supports per minute. But we know that each scooter needs one support and two ribs. So if we consider component set that includes two ribs and one support, obviously that makes more sense. So if we do the capacity calculation for the component set, we get 0.3125 component sets per minute. So generally, capacity and batch sizes are related to each other as shown in the graph above. So as the batch size increases, capacity goes up. Another point to remember is that the process capacity can never be more than 1 by P, or 1 by processing time. Batch size can have an impact on where the bottleneck is. As you can see in this example, when the batch size is 12, milling machine has a capacity of 0.0833. Since this is lower than 1 by 3 capacity for assembly, milling machine becomes bottleneck when B equals 12. But the situation is different when B is 300. Now we have a smaller capacity, 1 by 3 for assembly, and assembly becomes the bottleneck. So the question is, what is the smallest batch size that the milling machine does not constrain the process flow? So here we are targeting a capacity of 1 by 3 units per minute, or 0.33. Capacity of 0.33 corresponds to a batch size of something between 100 and 150. So note that we are using 1 by 3 because anything less than that makes milling process the bottleneck. So the question is, what is the minimum batch size that yields the target capacity of 1 by 3 units per minute? So to find the batch size, what we can do is we can use this formula, and by solving for batch size we get this new formula. And if we replace the values for capacity, which is 1 by 3, setup time, which is like 2 hours 120 minutes, and processing time is like 2 minutes, we get a batch size of 120. So this will ensure that the milling machine's capacity is equal to assembly capacity. Next, let's look at interplay among batch size, idle time, utilization, and inventory. So idle time is basically when nothing is being produced. It can have two parts. Either there is a setup going on, or it is just idle time where there is no production, not even setup. Utilization is time which is used for producing divided by time producing plus idle time. When we increase the batch size, we increase the utilization of milling machine up to a point when it is no longer a bottleneck. But when batch sizes go up, inventory also goes up. So when we reduce batch size, it helps to reduce inventory. And we also know that when we reduce inventory, it reduces flow time as per Little's law. So let's consider this example of a small batch where we have 80 component sets. With 80 component sets, milling process becomes the bottleneck because it needs 280 minutes to produce this batch, whereas assembly needs only 80 times 3, 240 minutes. So you can see that assembly will have idle workers about 40 minutes of the time during this production cycle. So the utilization for assembly is 85.7%, whereas milling, which is the bottleneck in this case, has a utilization of 57%. For a large batch of, let's say, about 200 component sets, assembly will need 200 times 3 minutes, so total of 600 minutes to produce 200 units. So we can see that assembly is going to be busy all the time, whereas milling machine will be idle for about 80 minutes. So utilization for assembly will be 100%, but utilization for milling machine will be about 67%. And finally, when the batch size is 120 component sets, assembly is going to take about 360 minutes to produce these units. And you can see that assembly will be busy all the time, and also milling machine will not have any idle time. So if you calculate utilization for the assembly, it's 100%, and utilization for milling is about 67%. We cannot do better than this. So milling utilization cannot be more than 67%. Otherwise, milling's production is going to be more than that of assembly, and this is going to create a situation where inventory is going to just keep on growing, which is not a desirable situation to have. When we look at inventory pattern, where we have 200 component sets and the flow rate is 1 by 3, we get this picture. So the blue line is the rib inventory. So as the production of ribs continue, the line keeps on going up because we are building inventory. This is slightly different from the earlier inventory pattern where we received the orders from an outside supplier. So as soon as the order comes, inventory jumps to that quantity queue. But in this case, because as the production is continuing, it is also being utilized at assembly. So we don't see this blue line reaching 200 components. Similarly, when the production of ribs stops and production of support starts, we start building inventory for the steer, which is represented by red line. And at that time or during that period, the blue line keeps on coming down because the inventory is depleting. Now, suppose we have a component set of 200 units to produce and flow rate is 1 by 3. We start the production when inventory level is 0. In 200 minutes, we can produce 200 repairs, whereas the demand for repairs from assembly is 200 times 1 by 3, which is the flow rate, about 67 repairs. So the inventory at the end of the production is 200 minus 67, which is 133. So 133 is the maximum inventory level for ribs that will be reached. So if you divide 133 by 2, we get about 66 units as average inventory. If we do similar calculation for the recommended batch size of 120 units, which is number of component sets with a flow rate of 1 by 3, what we get is the maximum inventory that will be reached is 80 units and average inventory will be 40. So this will be more efficient. And if inventory level were any lower than 80, then the milling machine is going to become the bottleneck. Next, let's consider how to minimize inventory when there is product variety. So in this example, we have two soups. chicken and tomato, and also their demand, setup time, and production rates are given. So we are defining the flow unit to be 1 gallon of soup, and we are assuming that we can iterate between chicken and tomato production. Of course, the setup time will be needed when we change from one to the other, and the batch is being defined as the total quantity in gallons. So, what batch size will minimize inventory? That's the question we want to answer. So, to find the batch size, first we find out what is the target capacity, which in this case is the total demand, which is 100 plus 75. The total setup time is 2 times zero point 0.5 for each type of soup. So, the total is 1 hour per batch. And since the production rate is 300 gallons per hour, we take the reciprocal of that to get processing time of 1 over 300 hours per gallon. So plugging in the values, we get a batch size of 420 that will minimize the inventory. And we can proportionately divide this 420 between chicken and tomato soups by taking ratio of demand over total demand and then multiplying that by batch size. So we get 240 gallons for chicken and 180 gallons for tomato soup. We can extend this to three soup situation, and we can calculate what batch size minimizes inventory by doing similar calculations. Now we get a batch size of 630. So this is about 50% increase compared to the earlier batch size that was recommended. And you can also see how many gallons should be produced in proportion to the demand for chicken, tomato, and onion soups. Now let's consider a situation where we have total demand which is more than 175 that we had earlier. The total capacity that we need is 225 gallons per hour. Total setup time is now going to be 1.5 hours per batch. Processing time is still 1 by 300. So we get a batch size of 1350, which is 221% increase compared to earlier number. So we can divide this 1350 into proportional demand. So this is a famous quote by Henry Ford. They used to make cars only black in color, and the idea behind that was if there are different colors, so obviously it will take time to change from one color to the other, and utilization of the process is going to decrease, and especially when demand is very high, tendency is to maximize production. So to summarize, when we have setup times involved, capacity depends on the production schedule. We know that when we increase the capacity, the batch size gets larger. You can remember this picture. When the batch size increases, capacity increases, but the capacity is limited by 1 by P, where P is the processing time. But also note that when batch size gets larger, inventory also increases. Utilization may increase as the batch size gets larger, and there is always a trade off between capacity and inventory that we need to do. And this formula for batch size also points out that batch size is proportional to setup time. So if we can reduce setup time, we can also reduce batch size. And the last point indicates that long setup times are not compatible with large product variety. So we need to have smaller setup times to be more flexible with the production. Here, since first unit will take 1.1 minutes, so the optimal batch size will be slightly more than 41, so we approximate it to 42.